Welcome to the Problems Channel Season 2, Episode 11, the episode in which we will discuss the solution of the mathematics problem S2M13. But before we do that, as a traditional friendly reminder, if you are joining our channel mid-season, then first of all, thank you very much for your vote of confidence. And second of all, it is a good idea to go to the channel's homepage and in the channel's trailer section, find the episode titled The Problems Channel How To, and watch that episode in its entirety, because in that episode we explain and motivate everything that we do on this channel. As a refresher, the mathematics problem S2M13, which we will be solving in this episode, is apparently at least 1230 years old and has a quite rich historical background, which I painted in broad strokes in the previous episode. As a quick refresher, in the lightning round, this specific problem apparently was the problem number 18 in a collection of, depending on who you ask, 52 to 56 problems that were gathered in a book whose title is shown over here in Latin. In English, in my interpretation, the title of that book reads A Collection of Problems or a Collection of Puzzles for the Overall Intellectual Development of Young People. That book apparently was published in the year of 795 of Common Era by this gentleman over here, and again, apparently, and to the best of my knowledge, this here gentleman was a scholar and perhaps a member of the royal or the imperial court of this gentleman. His name is shown over here, and below I showed the years when this person lived. Apparently, in English, we could agree to pronounce his name as Karl the Great, who was a big-time, big-shot figure who affected the overall development of Europe in general and of Western Europe in particular. And among other various things, he's also known for the initiative to create the first ever, apparently, that is a claim that needs verification, but apparently Karl the Great was the first person in Western Europe to create or show the initiative for the creation of the first ever organized academic and educational institution in this here German town in this same year of 795 of Common Era. In detail, in the mathematics problem S2M13, we're given a group of 4 objects: 1 human, a peasant, 2 animals, a goat and a wolf, and 1 vegetable, a head of cabbage, and we're told that this merry company is traveling, let's say, from point A to point B, and on their journey they come across an obstacle, a river, and on the same bank where they find themselves at the moment, there is a rowboat that can fit at most 2 objects in it at a time. As the intellectual challenge in this problem, we're asked to design a crossing scheme which will allow the peasant to move each and every member of his company safely across the river in the minimal number of crossings if it is known that there are 2 conflicts or 2 incompatibilities in this group. That is, if the goat and the head of cabbage are left alone without the adult supervision of the peasant, then the goat will eat the head of cabbage, and that is not acceptable, because one of the requirements of this problem is to make sure that each and every member of this here company makes it across the river safe and sound in one piece. Likewise, if the wolf is left in the company of the goat without the adult supervision of the peasant, then the wolf will snack on the goat. That is also not acceptable, because again, each and every member of the peasant's team has to make across the river safe and sound in one piece. Those of our viewers who practice mathematics correctly and do that in the fashion that we described in Season 1, Episode 2. No doubt, during the fourth stage of practicing mathematics correctly, try to abstract and generalize the solution of this problem that they just generated. During the attempt to abstract that problem, these viewers who solve this problem correctly and on their own, give or take more or less, or essentially and fundamentally, had no choice but to discover the problem solving approach, to which I refer as the space-time problem solving approach. The name that I gave to this specific problem-solving approach, space-time, is admittedly a bit pretentious. But this is the best that I could do, and if you think that you have a more fitting name for this problem-solving approach, then by all means, do not be shy, be my guest, and share your good ideas with me and the rest of us in the comment section to this episode. Meanwhile, in my problem-solving adventures, I have noticed that in certain technical problems with a pronounced spatial and temporal interaction between their various components, in the classical physics limit, there exists only four interesting pairings between the two fundamental notions of space and time. And I have captured these four pairings for your convenience in the table shown over here. That is, the events of interest in this or that technical problem and or the objects of interest in this or that technical problem can happen or interact with each other at the same time and in the same space as captured by this square over here. They can also take place at the same time but at different space as shown by this square over here. These events can also happen at different time and in the same space. And lastly, they can also take place at different time and at different space. We also know now that under the mathematical model or in the special relativity, special theory of relativity case due to Einstein and company, if two events took place in two distinct points in space, then it becomes impossible to judge in the traditional or classical absolute sense whether these two events took place simultaneously or at the same time. And thus, we now understand the limitations of these possible pairings, with only one notable exception in the relativistic case, that is the fact that two events happen simultaneously at two distinct points in space is still detectable under the formalism of the special theory of relativity when the reference frame of interest is moving strictly orthogonally or perpendicularly to the straight line that connects the two points in space of interest. Consequently, this matrix, or let's say space-time matrix, applies only in the case of velocities that are small enough when compared to the speed of light in vacuum and in the presence of small enough masses, and under the sole exception in the relativistic case when again a frame of reference of interest is moving strictly perpendicularly or orthogonally with respect to the straight line that connects the two points in space of interest. Consequently, the space-time problem-solving approach suggests or recommends that whenever we come across a technical problem with a pronounced spatial and temporal interaction between its main components, we simply keep this space-time matrix front and center, and we analyze the various events and the interactions between the various objects of the given problem for the question of whether these interactions are advantageous or not advantageous when it comes to the space-time pairings shown over here. And yes, some of our viewers may even think that this problem-solving approach is not as much a problem-solving approach as it is simply a reminder. However, I would like to notice that for something to be useful and powerful, that something does not have to be complicated. Sometimes simple does it. And in order to show how the space-time problem-solving approach was already applied in practice at least once, let us take a brief look at the case of the so-called Caspian Sea Monster, or a ground effect aircraft. As a 30 seconds or less crash course on ground effect, from your college days you may remember that the angle between the so-called chord, or roughly, let's say, this line right here, and the direction of the oncoming flow of air, let's say if this direction is like this, so this angle right here, this angle, let's say alpha, is known as the angle of attack, and that is one of the crucial or necessary components of the overall hardware design of an aircraft that generates this magic phenomenon known as a lift. And let's say that for the sake of demonstration, we'll just take one molecule of air, and when such a molecule of air hits the bottom surface of the aircraft's wing, let's say, again, for demonstration purposes, it doesn't have to be obviously that way. The actual phenomenon is way more complicated, but for demonstration purposes, let's say this molecule of air reflects off of the bottom surface of the aircraft's wing in the downward direction over here. In a traditional aircraft that is flying way high above the ground, there is absolutely no chance that that molecule of air will ever reach the surface of our planet because it's just way too far. However, if such an aircraft is flying very close to a so-called screening surface, right here, let's pretend that this is the screening surface, and the role of the screening surface can be played by the solid ground or by the deep enough and large enough body of water. Consequently, when such an aircraft is flying very close to such a screening surface, and again, how close is close? Well, technically, if we get to the nitty-gritty mathematics of the ground effect, then there are formulas that predict with high degree of precision at which specific height the ground effect becomes noticeable and pronounced. For us, is just enough to say that in absolute terms, it could be several meters off the ground, or in general, that height is connected to the characteristic feature of the wing called the chord. But the bottom line, technically, for us, what is important, that if an aircraft is flying close enough to the screening surface shown over here, then our proverbial molecule of air has enough time to get reflected off, or gets bounced off that surface and reach the bottom surface of the wing one more time. And again, in essence, for demonstration purposes, of course, we will understand that the actual phenomenon is way more complicated, but this episode is not about the mathematics of the ground effect. this is an episode about the mechanics of the space-time problem-solving approach. So as a first approximation, motivation for why ground effect takes place, this is enough for us to understand that if the aircraft at hand is flying close enough to a screening surface, then our proverbial molecule of air has enough time to bounce off of not only the wing but off the screening surface, come up and hit that surface again, and thus provide additional lift. Now, some number of engineers in some number of countries try to design the ground effect airplanes that were destined to fly over the surface of water. And historically, all these engineers faced one and the same problem that proved to be very difficult to solve. And that was the problem of unsticking the body of the ground effect aircraft off of the surface of the water over short enough distances with very low initial velocities and with expending reasonably small amounts of fuel. In other words, practically yes. In some countries, some engineers managed to put together such a ground effect aircraft that was able to take off eventually from the surface of the water, but these distances were just impractically long, and overall process took way too much fuel, and that constituted, let's say, a failure in such a design. And until that is a solution came, and that solution was precisely in the spirit of the space-time problem-solving approach. And for you to try to come up with that solution under our guidance, we suggest that you play the role of, let's say, a chief designer of an aircraft design bureau and look at this aircraft that we show over here. Over here, and over here. And now that you have seen all these traditional aircraft, take your time. We understand this is new material, this is complicated, this is not easy. Feel free to put this video on pause, walk away, think about it, but when you come back, do tell us what one relevant characteristic feature of the designs of all these aircraft do you see, and what that characteristic feature has to do with the main components that make up the object of interest or a ground effect airplane. Yes, this is precisely what we wanted to hear from you. In each and every aircraft design that we showed earlier, the respective wing and the corresponding engine enter into the mutual relationship in the same time, same space pairing. That is, each and every wing with the corresponding engine form one and inseparable whole and are located in the same space at the same time. However, a admittedly beautiful and elegant solution to the problem of unsticking a airplane from the surface of the water at low velocities came from the design bureau that was led by this gentleman over here. In Russian, his name pronounced as Rostislav Evgenievich Alexeyev, and he lived between the years of 1916 and 1980. And again, I do not know if the upcoming idea was purely his idea, or as it usually happens, it was a result of a collaboration between several engineers on his team. I tend to think that it was probably the latter. It was the collaboration between the different team members that was led by this gentleman. But their elegant solution came down to transitioning from the same time, same space pairing of the engine and the wing to same time, different space. That is, the engineers on the team led by this gentleman unbuckled or separated the wing and the engine in space by but not in time, as shown over here, and over here, and over here, and over here. You see, at this initial state of affairs at low velocities, the surface of the water with a large, let's say, boat submerged into it acts as a sort of lightweight glue or a viscous, gooey, swampy substance that does not want to let the fuselage of the ground effect aircraft go. Consequently, in order to escape the grip of the water in this initial state of low initial velocities, it would be nice to have some help. And this is where the idea of same time, different space shines. What the engineers led by this gentleman over here back around 1960s and then USSR did is that they separated the engine and the wing of such an aircraft in space, but not in time, by moving the corresponding engine blocks, as you saw in the photographs shown earlier, to the very front or the nose of the aircraft, and by pointing the exhaust nozzles of these engine blocks to direct the airflow when the engines are turned on, of course, directly under the wings, and thus provide the extra help and facilitate the unstickiness or unsticking the aircraft and getting it, helping it to get airborne. Schematically, again, for demonstration purposes, avoiding all sorts of gory and complicated details, that whole process of separating the engine from the wing in space but not in time can be portrayed as follows. And now, when we step back and look at the solution of this problem, we cannot help but to think, gee, that was very simple. And you may have noticed that on this channel, I do not like to use the word simple at all, because in mathematics, theoretical physics, and computer science, nothing is really simple. Everything is difficult. Everything takes an effort. But again, for demonstration purposes, let us pretend that the solution that was offered by the engineering team led by the gentleman shown over here was simple. The question that comes up next is the following. If that was so simple, how come many people looked at one and the same problem and none of them came up with that simple solution? The answer to that question, whatever it is, has more to do with the psychology of solving technical problems, because more often than not, in the heat of the battle, so to speak, or in the adrenaline rush to find a solution to a technical problem, we somehow, for all sorts of fabulous reasons, fail to see something that is right, very close, or very nearby. And this is precisely the issue that the space-time problem-solving approach is designed to address, simply by keeping in mind that under conditions and limitations spelled out earlier, this and that pairings of events and or objects in a given problem can happen this or that way may help us find a solution of that problem. Now that we understand more or less how the space-time problem-solving approach may work in practice, and granted, this is difficult, this is not easy, this is new material, feel free to pause this episode and rewind it, watch it several times. But now that we have more or less a reasonable understanding of how the space-time problem-solving approach may work in practice, we will go back to the solution of the mathematics problem S2M13. In our problem, we do not have angles of attack, and in all its generality, we do not have nonlinear differential equations and partial derivatives. However, what we need to do in our problem is to not forget to practice mathematics correctly. And as we explained in season 1, episode 2, the first thing in practicing mathematics correctly is understanding the problem statement correctly and deeply. What does it mean in this problem? In this problem, we want to understand what is the nature of the conflict between the goat and the cabbage and the wolf and the goat. What is the technical essence of this situation when we say that these objects at hand are not compatible? Well, now that we know a little bit about the space-time problem-solving approach, we know that the technical essence of this incompatibility or of this conflict is exactly reflected by the pairing of the main objects in the problem that corresponds to same time, same space. In other words, if the goat and the cabbage find themselves at the same space at the same time, we have a problem. And likewise, if the wolf and the goat find themselves at the same space at the same time, obviously without the adult supervision of the peasant, we also have a problem. And how do we solve this problem? Well, just like in the previous example of the ground effect aircraft, we know that by transitioning from same time, same space into the different space, same time, then we resolve that conflict. But in this problem, we're also told that our rowboat can carry at most two objects at any given time. Consequently, we want to scale the amount of combinatorial work that we have to do, because in general, before we begin solving this problem, or as we begin solving this problem, we want to generate all the possible two combinations of the objects at hand, or because this capacity over here deals with at most, then in general we want to generate 0 combinations, 1 combinations, 2 combinations, and if we were to deal with the problem with a larger number of objects and with perhaps a higher capacity of the carrying vehicle, we would be also on the hook to generate 3 combinations, 4 combinations, 5 combinations, and so on. And what are these K combinations? Well, these K combinations are technically subsets or arrangements of objects in which the notion of order is irrelevant. Indeed, if we put, let's say, a peasant and a goat into our rowboat over here, this is the same thing as putting a goat and a peasant into a rowboat. Consequently, when the notion of order does not apply to the arrangements of objects, we refer to these arrangements as subsets, and the number of such subsets, as we remember, is given by the value of the corresponding binomial coefficient n choose k, and in our case that is 4, n is equal to 4 because we're given 4 objects. choose 2 because we can fit at most 2 objects in our rowboat, and we know that value very well. 4 factorial over 2 factorial times 2 factorial, that's 24 over 4. That will be 6. And mercifully, that number is quite small, even though that we know that there are various computer science algorithms that will allow us to automatically generate the respective permutations and or combinations of objects. Here we pretty much play out one of these computer science algorithms by hand by beginning, for example, with the peasant. Also, we'll agree to designate the usual suspects in this problem by their first characters in their name because there is no conflict. With P, we'll designate the peasant. With G, we will designate the goat. With C, we will designate the cabbage. And with W, we will designate the wolf. As such, fixing the position of the peasant in the upcoming 2 combinations, we write them down. For example, let's say we pair up a peasant and a goat. This will be our first 2 combination or first 2 subsets. Then we pair the peasant with the cabbage and designate it with PC. Then we pair up the peasant with the wolf and designate this pair with PW. And now that we see that we have exhausted all the possible combinations in which the peasant takes the fixed position as the first element in the pair, then we move on to the next element, and let's say that will be the goat. Again, we pick the goat to be the first one. Here we have which choices? A goat and the cabbage. We designate the pair with C, GC. Then we have a choice for the goat and the wolf. We designate that pair with GW, and we see that we have exhausted all the possible pairs where the goat takes the very first position. We accounted for all such choices for the peasant. We have a combination of a goat and a peasant over here. And we move on to the last choice. Let's say we have a cabbage and a wolf. We'll designate this pair as CW, and we already see that we have done all the work for the wolf, and we simply carefully count 1, 2, 3, 4, 5, 6. We have generated all 6 pairs of the objects at hand, and now we need to see which such pairs even make sense or are legal in our problem. As we try to design our first river crossing, what we will be doing now is called elimination. And in general, elimination also deserves its own name because eliminate and conquer is a real thing. It's another problem-solving approach, which in general in Western literature, for example, was popularized by Arthur Conan Doyle through the words of his immortal character of Sherlock Holmes, who used to say that when everything that is impossible is eliminated, then whatever remains, however improbable, is the truth. In our case, how exactly do we eliminate the pairs of objects shown over here for the purpose of designing our first crossing? Well, every time we go through the pair that we generated combinatorially on the previous step, we consult our space-time matrix and see if that particular pair of the usual suspects in this problem makes sense and satisfies the constraint of the problem. Well, we see that every pair where the peasant participates as the first element goes without a question because the peasant gets along with everyone without any problems. But in the second row, we see the pair where the goat and the cabbage and the head of cabbage are paired up. Is that pair legal in this problem? Well, according to our space-time matrix, if the goat and the cabbage find themselves in the same space at the same time without the adult supervision of the peasant, which is clearly absent in this case, then let me do it with the red chalk. We eliminate this pair. This is no go. Next, our next pair is the goat and the wolf. Again, if the goat and the wolf find themselves at the same space at the same time without the adult supervision of the peasant, which is obviously absent in this pair, then we have trouble. This is not acceptable, and we eliminate this pair as well. And lastly, we have the candidate where the head of cabbage and the wolf are paired up, and is this pair legal? Well, technically, that pair is legal, but even though we are not told explicitly in this problem that only the peasant can row the boat, here, and I mean this without any joke, as I will explain momentarily, we do entertain this idea. What if we do not eliminate the pair of the wolf and the head of cabbage right away, and we try to play with this idea? What if we put the wolf and the cabbage into the rowboat for the very first crossing of the river? What will happen then? Well, on that crossing, let's say we put the wolf and the cabbage. First time they go, number one. And what will happen? Let's say this is one bank of the river, this is the second one. What will happen over here? Well, let's say the wolf knows how to row the boat. They go across the river for the first time. Here, the cabbage will be the wolf will put the cabbage on the bank, jump in the boat over here, row back for the second time. The wolf only, that will be crossing number two. Here, which pairing will work when at this point, let's say in this point in time, we find whom? We find the peasant, we find the goat, and we find the wolf. Well, at this point over here, we know that, for example, the wolf and the goat pairing, which we eliminated, is not acceptable according to same space, same time pairing. So, for example, let's say a peasant gets into the boat with the wolf, rows across the river this way for the third time, where we have the goat over here, peasant and the wolf in the boat over here. These objects, the main objects of the problem, are separated in space at the same time. Everything is legal, everything is good. By the time the boat comes to the shore over here, the wolf jumps out of the boat and we have a wolf and the cabbage. At this point, the peasant turns around, goes back here for the fourth time, and at this point in time when the peasant arrives, there is the peasant and the goat. The peasant picks up the goat, puts her in the boat, crosses the river. This time it's the peasant and the goat for the fifth time. And here we find everyone: peasant, goat, wolf, and cabbage. Now, this solution takes 5 crossings. It never violates any of the constraints of the problem, but it does rely on the humorous and jokingly funny situation where we assume for a moment that the wolf can row the boat. This is actually not a joke, and I mean it very seriously, because overall in hard sciences there exists this idea. It is not as much of a problem-solving approach as it is an idea that sometimes it is possible to identify a conflict in the problem and then take that conflict all the way to the maximum amount or to the maximum extent possible. Sometimes, depending on our powers of perspicacity, creativity, ingenuity, and improvisational skills, it is possible to convert this absurd conflict into a technical, viable, and legal solution. Here, of course, we are not told explicitly that only the peasant can row the boat, but we all understand that this is the case. But we can draw certain conclusions from this humorous solution, and we will see what is going on with this humorous solution in our next attempt. Very well. In the previous segment, we have eliminated the seemingly obviously illegal choices, even though even that elimination we had to do carefully and with style, because as one of my math professors used to say, mess things up with style, which means that even when you mess things up, try to learn something from this mess up and take that information that you managed to extract from that failure into the next iteration of the solution of the problem. I have written the remaining pairs of objects at hand that are candidates for the first river crossing over here. And now we go through slightly more involved elimination rounds. Let's say we work our way right to left. What if we choose the pair peasant wolf for our first crossing of the river? Well, in that case, when we pick the peasant wolf pair, then according to our space-time matrix at the same space at the same time, we will have what? We'll have the goat and the head of Cabbage, obviously without the adult supervision of the peasant. That is not acceptable because as the peasant rows the boat with the wolf in it, the goat will happily snack on the cabbage. That is not acceptable. And again, let me do it with the red chalk. We eliminate the choice peasant wolf for our first crossing. Next, we consider the peasant and cabbage choice for the first crossing. In that case, if we pair up the peasant and the cabbage in the first crossing in the boat, then what we will have on the bank of the river here? Well, we'll have the goat and the wolf. And according to our space-time matrix again, the wolf and the goat in the same space at the same time, obviously without the adult supervision of the peasant, because the peasant is rowing the boat right now. That is a conflict, that is no good, that is eliminated as well. And what we see now, that after some lightweight combinatorial work and slow and thorough elimination rounds, we have one and only one candidate pair for the first crossing of the river, and that pair is the peasant and the goat. If we pair up the peasant and the goat for the first crossing, then at the same time in the same space, these two objects will be in the boat, and what will remain on the shore? We'll have the cabbage and the wolf. These two objects are not in conflict. Everything is good. Consequently, we will begin recording our solution as follows. Let's say in the initial moment in time, we had the peasant, we had the wolf, we had the goat, and we had the cabbage on the bank of the river here. We'll designate the other bank with this line right here. With the dashed line, we'll designate the process of splitting of our company. So at that moment, when we put the peasant and the goat into the rowboat, who do we have? We have the wolf and we have the cabbage on the shore. We have here for the crossing number 1, we have the peasant and the goat. We again analyze this state of affairs against our space-time matrix. Everything seems to be good. So by the time this dynamic duo arrives at the opposite bank of the river, we will have the peasant and the goat on that side of the bank of the river, the wolf and the head of cabbage on the opposite bank. Everything is good, there is no conflict. Here we'll designate another transition corresponding to a split, so that at this point these guys split, and we have the goat on that side with this at this stage. And for the crossing number 2, we have only the peasant going for the crossing number 2 over here. And at this time, we also have the wolf and the cabbage on this bank of the river. By the time the peasant arrives, what do we have? Here we will have the peasant, the wolf, and the cabbage. Again, at each stage, we run our problem or troll our problem through the space-time matrix, validate the situation. We see everything is cool. Again, here we split. What are our choices for the crossing number 3 over here? Well, if we put the wolf in the boat with the peasant for the crossing number 3, we will have the head of cabbage on this side of the river. The goat will be over here. That seems to be working, but we also think that we can, instead of putting the wolf in the boat, we can put the head of cabbage, even though we may think, they may be in conflict over here. So for now, we will try to put the wolf for the crossing number 3 over here in this direction. We'll put the peasant and the wolf. At this point, we will have the cabbage on this side of the river. We have, by the time the peasant and the wolf arrive on the opposite bank of the river, we'll have the peasant, the wolf, and the goat. Here, with this choice, in my personal experience, this particular state of affairs presents a challenge to many people who try to solve this problem, because somehow they think as follows: now that the peasant brought the wolf and to the opposite bank of the river, we have the wolf and a goat. According to our fancy schmancy space-time matrix, these two guys are in conflict. So if the peasant turns around and goes back, this is not possible. Oh my God, this problem has no solution. Here again, it is interesting how the psychology or human psychology comes into solving problems. Some people give up, some people do not give up. What we can say over here is to remember the advice of Gregory Poya from his immortal book, How to Solve It. And that advice comes in the form of a question: have you used all the data? And apparently the people who give up solving this problem at this stage have not used all the data, because what we're given is that the fact that the rowboat can hold at most 2 objects at a time. So here we do not really have a conflict, and we can avoid the conflict, because remember, the boat can fit 2 objects in it at any given time. So here we do a switch. Here we leave here we perform a split. So we only leave a wolf on that side of the river, and we put the peasant and a goat back into the boat, and we cross the river for the 4th time. By the time we arrive at our original bank of the river, what do we have? We have the peasant, we have the goat, we have the head of cabbage, we have the wolf happily on the other side of the river. Everything is good. The potentially conflicting situation between the goat and the cabbage is resolved by the presence of the peasant. And what do we do now? Well, again, in some sense, what we do over here is we fall back onto our humorous solution, which took 5 crossings, where the wolf rowed the boat originally. And we remember that in that humorous solution, on the last crossing, or on the crossing number 5, the peasant and the goat crossed the river. But in our real and legal solution, the peasant and the goat went first for the crossing number 1. Likewise, over here, we again perform a switch, and the way our happy company splits is as follows. We keep the goat on the original bank of the river. We put the peasant and the cabbage into the boat. We'll let the peasant row the boat and cross the river for the fifth time. And by the time this dynamic duo arrives at the opposite bank of the river, what do we have? Here we have peasant, wolf, and cabbage. Again, if we analyze this state of affairs against our space-time matrix, then we see no problems. Everything is fine. At this point, this group can split which way? Well, we keep the wolf and the cabbage, the head of cabbage, on the opposite bank of the river. There is no conflict over here. Then the peasant jumps in the boat and crosses the river for the sixth time. By the time he arrives, we have peasant and goat over here. And at this point, there is no other choice but to put the goat into the boat. And here we do just that. And we cross the river for the seventh time. This is the peasant and the goat. And by the time this dynamic duo arrives at the opposite bank of the river, what do we have? Peasant, goat, wolf, and cabbage. And the problem is solved in 7 crossings, and the state of affairs in each and every crossing is legal because we analyzed each such crossing against the space-time matrix that we constructed earlier. And the question now is this solution unique, or does there exist another solution to this problem? Before we begin searching for the second solution of this problem, let us pause for a moment and step back into the first solution of this problem. For example, let's concentrate on the result of the third crossing of the river over here, when we had a potential conflict between the wolf and the goat. How did we resolve that conflict? We resolved that potential conflict by separating the objects that are in conflict in space but not in time. And what does that mean? Well, when we say that we separated the wolf and the goat in space but not in time, that means that we let the wolf hang out on the opposite bank of the river over here, and at the same time the goat was enjoying the safety in the company of the peasant over here. Likewise, when we had the potential conflict between the goat and the cabbage over here, what did we do? Well, technically, we separated the conflicting objects, the goat and the cabbage, in space but not in time by performing a swap and putting the head of cabbage into the boat in the company of peasant and letting the goat hang out on the original bank of the river. Next, when we are searching for the second solution of the problem, we go back again to the first solution and try to find if there is any leeway for an alternative way of arranging the objects at hand. Here we see that after the second crossing over here, when we find the peasant, the wolf, and the cabbage on the original bank of the river, in our first solution, we put the wolf into the boat with the peasant. But is that the only choice? Once we think about it, we realize that no, that is not the only choice. Instead of putting the wolf into the boat with the peasant, we might as well put the head of cabbage into the boat with the peasant, and that is what we do over here. I'll reflect a different solution with red chalk. Here we will keep the wolf. This time we will keep the wolf on the original bank. Then we will put the peasant and the head of cabbage into the boat for the crossing number 3. And by the time this dynamic duo arrives at the opposite bank of the river, we will have what? We will have the peasant also. We'll have the peasant. I'll put him in white. We'll have the cabbage. We'll have the cabbage. And we will have the goat as well. It's almost like the situation that we had after the third crossing in our first solution, except that this time instead of the wolf, we find the cabbage in the company of the goat and the peasant. Again, we have a similar conflict between the cabbage and the goat. We already know how to resolve it. At this point, we keep the cabbage we keep the cabbage on the opposite bank of the river. We put the peasant and the goat into the boat, let them cross the river for the fourth time, at which point, what will we have? We will have the peasant, the wolf, and the goat on the original bank of the river. We have a potential conflict over here. Again, we know how to resolve it. Here the company splits as follows. The goat remains on the original bank. The peasant and the wolf jump in the boat. Peasant and the wolf. They cross the river for the fifth time. Here on this bank we find the peasant, the wolf, and the head of cabbage. No problems here. The company splits. We have the wolf and the cabbage remaining. The peasant jumps in the boat and crosses the river for the sixth time. Here he picks up we have a peasant and the goat. Here he picks up the goat and crosses the river for the seventh time. Peasant and goat. There is nobody here. This is number 6. This is not a goat. And here we have peasant, goat, wolf, and cabbage, safe and sound, honoring all the constraints of the problem. The problem is solved. It turns out that this problem does not have a unique solution, but it has two distinct solutions, and we understand where the solutions branch. They branch precisely after the second crossing, as shown over here and over here. These are the difference. But if we analyze these two solutions further, we see that the seventh crossing is actually the same. The sixth crossing is also the same. And where do we have the differences? The differences are here on the third crossing compared to this one. And actually the fourth crossing is exactly the same. And again, the fifth crossing is where the differences are. Now that the problem is solved and we understand how this problem, how the solution was generated by a constant consultation with the space-time matrix, we can step back a little bit and do a simple counting arithmetic. Let me use the blue chalk, for example. We'll do it over there. Let us count how many times did the peasant cross the river. Obviously, we don't really have to do too much work. We know that the peasant is present for each crossing. So for the peasant, for the number of crossings, we tally it up as 7. Next, let us see how many times, for example, did the goat cross the river in either solution. So this is the first crossing for the goat. This is the second one. This is the third one in the first solution. In the second solution for the goat crossings, we have 1, 2, and 3 again. So either way, the goat crossed the river 3 times. Now let us see how many times did the wolf cross the river here. Wolf once, nowhere again. And over here, wolf once, never again. So the wolf crossed the river once. And what about the head of cabbage? Again, scanning our solutions, we see that the cabbage crossed the river once in this solution and once in this solution. So the cabbage crossed the river exactly once. And if we think about it, then, for example, that's another way in which we see that, for example, the theory of graphs is practically born quite naturally from doing seemingly simple mathematical problems. That is, let's say we try to depict what's going on between the goat and the cabbage and the wolf and the goat. Well, these are the fundamental building blocks of the theory of graphs. And these are the nodes and the edges that form a graph in the theory of graphs. For example, if we depict with the node or the vertex um, the object at hand, the goat, and then with the edge we will capture the relationship of in conflict. Then we will see that the goat is in conflict with the wolf, and the goat is in conflict with the head of cabbage. In this specific problem, the goat is a bad girl. She cannot get along with anyone over here except for the peasant. And perhaps in this scenario, it also explains why the goat crossed the river 3 times and the other objects in the problem crossed the river only once. Now, this is it for this problem, and next we will look at the next challenge. Before I formulate our next challenge, please allow me to say a few words about the title of this episode. It is evident that I have titled this episode as Peasant, Goat, Cabbage, Wolf, and it is now evident why I have done it, because the problem that we just solved dealt with the peasant, the goat, the cabbage, and the wolf. But because we already have studied the reinterpret and conquer problem solving approach, we remember that each and every technical problem, for example, every problem in mathematics, consists of 2 parts: the technical essence or the core of the problem, and that technical core is dressed up into different material, and by very definition the variance of that material does not affect the technical essence of the problem at hand. It should be understood that the problem that we just have solved also has its own technical essence, and it has the language into which that essence was wrapped that can vary. For example, instead of the goat, we can use a chicken. Instead of the cabbage, we can use, let's say, chicken feed. And instead of a wolf, we can use another predator like a fox. And we can formulate pretty much exactly the same problem, but in terms of a peasant, a chicken feed, and a fox. And you are invited to find all sorts of other formulations of this problem, but we now understand that no matter how we dress up this particular problem, into which language we wrap its essence will remain the same, and hopefully we captured that essence by trolling this problem through the space-time matrix. Our next problem will be problem in mathematics, even though, again, feel free to disagree with me. You can claim that this is a computer science problem by all means all day long, but I will refer to this problem as S2M14, where M designates the problem in mathematics. It doesn't really matter, but in this problem we're given 12 visually indistinguishable coins, out of which only one, it is known that only one coin is fake or is not fair. The quality of this fake coin is also not known. In other words, we do not know whether the not fair coin is lighter than the real ones, or if the not fair coin is heavier than the real ones. We're also given one pen scale, and we're given one copy of pen scales, and we're told that in 3 weighings we are to discover the fake coin, the identity, and we are to discover its quality, whether that fake coin is lighter or heavier than the other ones. And by pen scales, we mean a mechanical contraption that looks as follows, and it has the pivot point over here. Everything else is more or less rigid, but the idea here is that there are only 3 outcomes of any weighing or any measurement, let's say, or any experiment. the pen scales shown over here can remain balanced, or each one fixed. For example, let's say the um, left pen scale can only go down or up, and consequently the right one can go up or down. And that is the technical essence of this contraption called the pen scales. Again, one more time, out of 12 visually identical and visually indistinguishable coins, it is known that one is fake. Its quality, whether it's heavier or lighter than the real ones, is not known. We're given one copy of pen scales, and in 3 weighings, we are asked to identify the fake coin and identify its quality. In other words, in this problem, we are asked to recover 2 units of information: the identity of a coin and its quality, whether it's heavier or lighter than the real ones. And again, my claim is that in general, this problem also has a lot to do with the space-time problem solving approach. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will discuss the solution of the problem S2 and 14.